So part D says for us to find the average rate of change of f on the interval from -4 to 3. So first off, to find the average rate of change, that's just the slope between the point at -4 and the point at 3. So we will do f of 3 minus f of -4. I assume you did this part. Over 3 minus -4, which gave us, what was f of 3? F of 3 was -3. F of -4 was -1 over 7. So what is that? That's I wrote a 3, even though I said 7. What is that? -3 minus -1. That's a -2 over 7. Okay. So is that what you got? -2/7?
Yeah.
Okay, good. And it says then that there's no point C on that interval for which f prime of C is equal to that average rate of change, which you can tell is true because all of these slopes are positive, right? And then this slope is not -2/7. It's just a linear piece that is, I don't know, looks like, what is that? 1, 2, 3, 4, 5, looks like it's -2. So clearly that's true. And the reason why that doesn't contradict the mean value theorem, the initial conditions of the mean value theorem is that the function must be continuous and it must be differentiable on the interval. And while our function is continuous on the interval, our function is not differentiable right there. And so the hypothesis of the mean value theorem is that if a function is continuous and differentiable on this interval, then the average rate of change must equal the instantaneous rate of change. Well, because we have a place where it's not differentiable, the hypotheses or the initial criteria of the mean value theorem aren't met, and therefore it's not guaranteed, so it doesn't contradict the mean value theorem. Does that make sense?
Yeah, it does.
Wonderful. Yeah, so done. Is it considered a corner? It's I guess, yeah, sure, we can call it a corner. It's not a cusp. It's not exactly a corner. It's kind of halfway in between. It's probably, honestly, I don't know what they specifically would define that as. I think corner is probably good enough, but you can just say a point where it's not differentiable. At x equals 0 would be fine also. Yep. All right, anybody else have any other questions on any of the graph FRQs before we move on to the multiple choice miscellaneous questions? Which I realized during second period, there's quite a few of them, but like there's a pretty big chunk of those that are BC only. So it's not as bad as I thought it was. All right, so let's start the multiple choice then. Just type them in the chat. So number 3 wants us to find the limit as x approaches 1 from the left of, I hate when they do these because they don't ever do this on the AP test, the greatest integer function minus the absolute value of x. So they want us to find the limit as we approach 1 from the left. All right, so let's think about what this looks like here. We should just be able to do the limit as x approaches 1 from the left of the greatest integer function minus the limit as x approaches 1 from the left, not negative 1, but 1 from the left. I should look that up there. 1 from the left of the absolute value of x. We'll just separate into two different ones. As we approach 1 from the left for x, or for the absolute value of x, that's just 1. And then as we approach 1 from the left of the greatest integer function, now the greatest integer function looks like this. be fairly familiar with this. We've talked about it a couple times this year, but you should have covered it last year. As we approach 1 from the left, we're at 0, so that should be 0 minus 1 or negative 1. Any questions there on number 3? All right. Oh man, we got a lot of questions. There's way more questions than we had last period. All right, next one is 22. So 22, we've got y equals x squared. We got y equals 6x, negative 6x, 6x minus x squared. And we're rotating this region between them around the x-axis. X squared looks like this. 6x minus x squared looks like this. We should sort of just know that, right? We know it's a parabola that's concave down, facing down, and we know that if we factor 6x minus x squared, we get x-intercepts of 0 and 6. So we want to find the ring as we rotate this around that has the largest area. And so the rings that we get should have an area of pi times the outer radius squared, which is 6x minus x squared, minus the inner radius, which is x squared. So this is the area of any ring. We want to know when is this at a max. So first, let's simplify it. Pi times 36x squared minus 12x cubed plus x to the 4th minus x to the 4th. Or area is pi times 36x squared minus 12x cubed. Everybody good with that being a formula for the area of any ring that we get when we revolve that around the x-axis? Okay, and then to find out when that's at a max, we take the derivative, set it equal to 0, and then the pi becomes insignificant. This just becomes, we'll take out a 36x and get 2 minus x. We want to know when does that equal 0? Well, at x equals 0 and at x equals 2. Clearly, it's not going to be at x equals 0 because that's going to be a minimum. X equals 2 makes sense. Let's double check either using a Sine chart or using the second derivative test. I'm going to use the second derivative test. A double prime of 2 is pi times 72 minus 72 times x, which is 2. So this is less than 0. Less than 0, we're using the second derivative test, tells you that it is a max. Since we had a critical value of 2, gives us a max. So x equals 2 is where we have a max. Good or no? Questions on that? All right. Next one is 36. 36 is kind of an annoying one. We got the limit as h approaches 0 of 1 over h times the integral from pi over 4 to pi over 4 plus h of sine of x over x dx. And so we're going to try and find a little bit better way to write this thing. What I'm going to do is I'm going to define our sine of x over x as the derivative of some function. Right? And we want to integrate that function. Since we don't know how to integrate sine of x over x. We're just going to say it's the derivative of some capital F function. So when I integrate capital F prime, which is sine x over x, I should get the limit as h approaches 0 of 1 over h times the integral of sine of x over x, which is the integral of capital F prime, should be capital F, evaluated at pi over 4 plus h, minus capital F evaluated at pi over 4. Everybody good with that so far? Okay. Now we get to use this nice little trick here. I'm going to bring that 1 over h all inside of here. And what is this? This is the limit as h approaches 0 of a function at x, some x value, plus h, minus that same function at x, all over h, right? This is the limit as h approaches 0 of f of x plus h minus f of x all over h. This is just the limit definition of the derivative, right? Limit definition of the derivative says just take the derivative of your function, capital F, and evaluate it at that x value. So now we're just looking for f prime of pi over 4. Well, f prime was sine x over x, so this is the sine of pi over 4 over pi over 4, which is root 2 over 2, divided by pi over 4, or multiplied by 4 over pi, which would be 2 root 2 over pi. So a little bit of a convoluted one where you got to use the first part of the fundamental theorem, or sorry, the second part of the fundamental theorem of calculus, and then the limit definition of the derivative. I wouldn't expect to see something quite like that. I think the multiple choice is usually easier than that particular problem was. Any questions there on 36? All right. Cool, my pen's not working. That's fun. There we go. 62 is our next one. So for 62, we want to know at what point on the interval 1 to 1.5 is the rate of change of sine of x, so f of x equals sine x, equal to its average rate of change. So we're talking on the interval 1 to 1.5. So the average rate of change ought to be sine of 1.5 minus sine of 1 all over 1.5 minus 1. And so the rate of change of it is just the derivative of it. So that should be equal to f prime of x or cosine x. So this is just some number that you can get from your calculator. Set that number equal to cosine x on your graphing calculator. Just graph y equals this and y equals cosine x and see where they intersect between 1 and 1.5. And I don't remember what the answer was offhand. I think it must be, I don't know, what did it come out to be? D, it says in the book here. D 1.253. Does that make sense how to set that one up? Any questions on that? So average rate of change is equal to instantaneous rate of change. All right. Next one. 65. We have the, that'll be fun, the nth derivative of the natural log of x plus 1 at x equals 2. Okay, so let's see here. The first derivative of this ought to be 1 over x plus 1. Right? This is, we'll call this f prime. Our second derivative ought to be the derivative of this, which is negative 1 over x plus 1 squared. Our third derivative of this ought to be, let's see here, we'll take another negative, and then it's 2. So the opposite of that makes it positive. It should be 2 times x plus 1, and derivative of the denominator, times the denominator squared. So it's x plus 1 to the 4th, which becomes 2 over x plus 1 cubed. The fourth derivative should be the opposite of 2 times 3 times x plus 1 squared over x plus 1 to the 6th, which should be negative 6 over x plus 1 to the 4th. And hopefully by here, we can recognize a pattern here. I'm kind of surprised they have this in the AB section, not the BC section. But with any luck, we'd notice that we're always going to have an x plus 1 in the denominator here. And the first derivative had it to the first power, the second derivative had it to the second power, the third derivative eventually had it to the third, the fourth derivative to the fourth. So, we're evaluating. So let's write a generic formula first. It should be an x plus 1 to the n down here. And then in the numerator, we've got a positive, then a negative, then a positive, then a negative. So to make it change signs, we'd have to raise negative 1 to either the n minus 1 power or n plus 1 power. Right, if we did to the n minus 1 power, n equals 1 for our first derivative, that gives us negative 1 to the 0, which is positive. And then if n is 2 for the second derivative, it gives us negative 1 to the first, which is negative, and so on. And then in the numerator, our constants go up from 1 to 1, 2 to 6. And you can see that they've got these factorials in there for some of these. And so we should know what a factorial is, right? A factorial is, if I have 5 factorial, that's 5 times 4 times 3 times 2 times 1. And so 0 factorial, I'm sorry, I'm going with 0. 1 factorial here is defined as 1. So this could be 0 factorial or 1 factorial. This is also 0 factorial or 1 factorial. This is 2 factorial. This is 3 factorial. So we need to take a factorial of, let's see here. Well, if I say that it's n factorial, that would mean this would be 1 factorial, this would be 2 factorial, this would be 3 factorial. That doesn't work. So let's just subtract 1 from that, which would make this 0 factorial in the numerator, which is defined as 1. 1 factorial, which is 1. 2 factorial, which is 2. 3 factorial, which is 6. 4 minus 1, so that should make sense. So it should be something like this. And like I said, that is negative 1 to the n minus 1 could have been a negative 1 to the n plus 1, just depending on how you wanted to write it. And we're evaluating this at x equals 2. So this denominator should just be 3 to the n. So it should be negative 1 to the n minus 1 factorial over 3 to the n, which looks like that's choice C. I would be really surprised, again, if they asked you to do something like that on the AP test. But that's what. Does that make sense? Any questions on that one? Good stuff, getting you ready for next year, though. All right, 72. We've got a region bounded by y equals e to the x, that's this. Y equals 1, should be this, and x equals 2, which should be this. We're rotating that region around the x-axis and finding the volume of the solid generated. So this should be, hopefully we can do this in terms of washers. So we're taking this region, which the intersection here, if y equals 1 and e to the x's is 0. So it's going to be an integral from 0 to 2. Should be pi times the outer radius, which is e to the x, squared, minus the inner radius, which is always just 1 squared dx, or pi times the integral from 0 to 2 of e to the 2x minus 1 dx, if you multiply the exponents there on the power rule, which is choice C, it looks like. Any questions there on that one? All right. Next one, 74. 74, we've got a region bounded by secant x, and they've been so kind as to sketch it for you. I guess it doesn't really matter because they gave you a calculator by this point. The y-axis and y equals 4. Be cool if they defined this is the region that they're talking about, it would appear, even though they didn't really define it as such. They've drawn a little rectangle in here for you with the delta y here to indicate to you that you're going to need to do this in terms of y. And so we want to rotate this region S around the y-axis, which should give us a disk. It should be pi times the integral from the lowest y value. Well, the lowest y value there, secant of 0 is 1. So it should be from 1 to the highest y value, which is 4. And your radius here should be whatever x is. Well, if y equals the secant of x, then x ought to equal the inverse secant of y. And so that's what we need, is the inverse secant of y squared dy, and then you'll just integrate that on your calculator. And it looks like it came out to be 11.385. Any questions on that one?
This might be a stupid question, but can you do 1 over like arc cosine, because there's no like specific like inverse secant button, right?
Yep. Yeah, that should come out the same. Did that come out the same for you?
I think I tried, but I might have just punched something wrong when I did it. I'll try it again.
So, I mean, you can always do this. So this will, if y equals the secant of x, here's x, right? And secant of x should be y, so that should be hypotenuse over the adjacent. And so if we're talking about the inverse cosine, I mean, you can just use this right triangle. Should work out doing 1 over the inverse cosine, but you can also do 1 to 4 of, if you look at this, the inverse. You can use any value on here. So we could do the inverse cosine of 1 over y would also work.
Oh yeah, I think you have to do that because there's a domain error if you try to do 1 over arc cosine.
Oh, yeah, that would make sense because of the 4. So yeah, so you gotta switch it around this way. So that's a little annoying, but yeah, take a look at your, I mean, if x is inverse secant of y, remember this is just x squared, so anything for x will work. And in this case, x is also the arc cosine or the inverse cosine of 1 over y. You could, I mean, you could, come out and say that this is the square root of y squared minus 1 here if you wanted to also, and do it as like the inverse sine of root y squared minus 1 over y, or you could do it as an inverse tangent of root y squared minus 1, or you could do it however you want to do it. But you can use a right triangle to figure out what any of those arc cosines or arc secants and arc tangents and all that stuff is. Any questions there on 74 now? Everybody, I have 2 or 3 people have at least asked for that. So. All right. Next one, 76. We got an object in motion along a line. It has an acceleration equal to pi t plus 2 over 1 plus t squared. And we know it's at rest. So v of, let's say at rest when t is 1, so v of 1 is 0. We want to find the average velocity from t equals 0 to t equals 2. So first we need to write a velocity function, then we'll use the mean value theorem for integrals to find the actual average value. So v of t ought to be the integral of this, which ought to be pi t squared over 2. And the integral of this ought to be 2 inverse tangent t plus some constant. We plug in 1, we ought to get 0. So plugging in 1 here gives me pi over 2. The inverse tangent of 1 is pi over 4. So this is 2 times pi over 4 plus our constant equals 0. So we have pi over 2 plus pi over 2 gives us a constant of negative pi. So v of t should be equal to pi t squared over 2 plus 2 inverse tangent t minus pi. We want the average velocity. So the average velocity should be the integral. It should be 1 over, what was it, from 0 to 2, right? So 1 over 2 minus 0 times the integral from 0 to 2 of v of t dt. And let's see, looks like that comes out to be, according to this, 0.362. Any questions on 76? All right. Let's look at 78. All right. We've got an ellipse has a major axis of 20 and a minor axis of 10. I guess it doesn't really matter which way we orient it. Let's just orient it this way. The major axis is 20, so that'll be 10, and this will be negative 10. And the minor axis is 10, so this will be 5, and this will be negative 5. And we are looking for the maximum area of an inscribed rectangle. So in order to do that, the first thing we're going to have to do is we're going to have to write the equation of this ellipse. So we should know how to write the equation of this ellipse. It should just be x squared over half of the major axis squared plus y squared over half of the minor axis squared equals 1. That's just your standard form for an ellipse. And our area here, well, this distance we'll call x, and this distance we'll call y. So what do we have? We have 2x times 2y. So the area ought to be 4xy. And we'll just need to put that into terms of one variable. We can put it in terms of x or into terms of y. It doesn't really matter. So I don't know, let's solve for y and put it all in terms of x, I guess. I don't know, what did they ask for here? They just said, yeah, the maximum area, so it doesn't really matter. So let's solve for y. So y is equal to 1 minus x squared over 100 times 25 square rooted. So our area should be 4x times the square root, and let's see, this square root of 25 is just, well, we'll multiply it through. So we got 25 minus x squared over 4. That should be 4x and 25 minus x squared over 4. And so all you need to do is, if they're looking for the maximum of this area, all you need to do is graph this function and see when it's at a max. You could take the derivative of this and see when it's equal to 0 and all that, but I mean, since you have a calculator, just graph that and see when it's at a maximum. And I don't know, it comes out to be an x value. I'm sure it's got it here in the book. No, of course they did it in terms of y. So I don't know what the maximum, the x value at which we have the maximum is. But that's fine. So you would graph this function which represents the maximum, or which represents the area, and the max would just be whatever the y value is when you plug this in. And so the max looks like it comes out to be 100. So you just graph this function. Good or no? And you might have to deal with your window settings. It'd probably be good to, you need to see when 25 minus x squared over 4 equals 0. So that'd be x equals. So you want to set your window probably from 0 to 10 on this, and then you probably have to set your y values quite a bit higher. Obviously up to at least 100 to see where that max occurs. So you just have to change the values in your graph to calculate that max. Does that make sense to everybody? Any questions on that? All right, next one is 80. 80 says we got f of x is 1 minus the integral from 0 to x of 1 minus 2 cosine cubed t dt from 0 to 2 pi. We want to know when is f increasing. So f is increasing if f prime is positive. And so we'll look for when is the derivative of this positive. So the derivative is 1 minus 2 cosine cubed t, since it's the derivative of an integral from a constant to x. We just want to know when is that greater than 0. So you'll just graph this function and see when it's positive. Find the x-intercepts of this function. And then anytime it's positive between 0 and 2 pi should be your answers. Does that make sense to everybody? So I don't know what let's see, it looks like it says that happens from 0.654 to 5.629. And technically, they'd want you to put this in brackets on the AP test. This book that I took these from is screwed that up and put them just as less than signs rather than less than or equal to signs. But on the AP test, since they're talking about when is it increasing, they would have definitely included those endpoints. Even though this is the correct way to do it would be with parentheses, but the AP test wants you to do it in brackets. So. Any questions on 80? All right, 82. Oh boy, a maple syrup storage tank that is 16 feet tall, hangs on a wall. The back of it is the shape of a parabola. Y equals x squared. All the cross sections parallel to the floor are squares. So they've drawn us this lovely little picture here. They got your parabola as your base, and basically you've got squares popping out of it that are perpendicular to the, they said perpendicular, they said parallel to the floor. And we have syrup that is pouring in. This is a large container. And man, I don't know why we need this much maple syrup. Syrup is pouring in at a rate dVdt of 12 feet cubed per hour. We want to know how fast in inches per hour, no, in feet per hour, is the syrup level rising when the height is 9 feet. So we're looking for dH dt when h equals 9. All right, this is a fun and exciting one here. So we need to find a formula to represent the volume of this thing. So in order to find the volume of this thing, we're going to do it in terms of y, because this cross section here has a very thin thickness to it in the y direction. And these are squares, so the area of this ought to be let's see, this is y equals x squared. This distance over ought to be x. Whatever we go over here ought to be x, which means that this length here ought to be 2x, which means that the area of the cross section ought to be 4x squared, which means that the volume ought to be the integral from 0 to whatever height we're getting to up here. So we're concerned about it goes from 0 to 16. We're interested in what's happening at 9, but we need a generic formula to represent 0 to any h value of 4x squared, which we'll have to deal with in a second, to turn into terms of y. And so if y is equal to x squared, then 4x squared ought to be 4y. So we should have the volume is the integral from 0 to h of 4y dy. Everybody good with that so far? All right. So dv dt ought to be the derivative of this. So the derivative of this ought to just be 4h times the derivative of h, which is 4h dh dt. And we have dv dt, which is 12. We're interested in a height of 9. 12 over 36 is 1/3 of a foot per hour, which I guess was answer choice B. Any questions there on that one? No, that's a square. So if it's 2x here, it must be 2x here, 2x here. So that's why we got 4x squared. Any questions on 82? All right, next one, 85. 85 gives us a 100-foot tall smokestack. And we are going to use a midpoint rule to approximate the volume of it, given a chart that has values of the height and values of the diameter. So it gives us 100, and it has a diameter of 5, 75, and it's 7, 50, and it's 9, 25, and it's 15, and 0, and it's 17. So to approximate the volume, we need to have an equation to represent, first off, the area of one of the cross sections of this thing, which looks something like this according to the picture. So the cross sections of it going up across the height, cross sections should be circular with an area equal to pi times the radius squared. So what we really want to do is we want to integrate from 0 to 100 pi r squared d, we call it dh because these are height values. But we need to approximate this using this integral using a midpoint Riemann sum. And it says with 4, yeah, it says using all 4 intervals. So really what we need is radii values, not diameter values. They're all going to be multiplied by pi, and they're all going to be multiplied by the 25, which is the length of the interval. So the first radius ought to be the halfway point between 15 and 17, which is 16, and then we'll take half of that, since that's a diameter, to get 8, and radius squared, so 8 squared. And then the next one is between 15 and 9, all that should be 12, and half of that is 6, so 6 squared. Next one is between 9 and 7, that's 8, and half of that is 4. And then 7 and 5, half of that, or that's 6, and half of that is 3. So whatever that all comes out to be, that's what, 125 times 25 pi, which, I don't know, what is that? 3,125 pi. My guess is that's probably closest to 9,800. Hopefully that's what the answer they gave us, but that's good there or no? Any questions there on 85? Y'all still there, right? Just making sure.
Yep.
All right. Good. Good news. All right. Next one is 93. So 93 says we got an outdoor concert. Crowd stands in front of the stage. They give us this little picture here. There's our stage, and there's our semicircle, it would appear, of crowd. This has a radius of 100. And the density of the people here is 20 over 2 root x plus 1. These are people that are x yards away from the stage. We'll just assume that's x yards away from like this center point of the radius there. We want to know about how many people are at the concert. So we're talking about these sort of like semicircular, I meant to do it in a different color, these semicircular regions going out, right, that have a very small thickness going out in terms of a change in x, and it should be, since these are semicircles, the area of each one of these little semicircles ought to be 1/2 of pi times that radius value here, which is the distance we are from the stage, which is x squared. And then we're going to have to multiply that by our density. And that ought to give us the number of people in each little very thin region. And then we'll just integrate that from people that are right up on the stage at 0 to people that are 100 feet away from the stage there. Everybody good with that? That's not right though. I did that wrong. Sorry. Now that I think a little more about that. That should not be 1/2 pi x squared. We're not talking about the area of each one of these. We're talking about, since these are so small and thin, we're talking about the length of this, which is the circumference, which should be 2 pi x for a full circle, right? 2 pi r divided by 2, since it's a semicircle. So it's the length of this times the density times the thickness of it, which is dx. So sorry, I screwed that up to start with. Everybody okay with that now? And then you have a calculator, so you can let your calculator do the work on integrating that for you. Which I don't know, what does that come out to be? Let me see here. Let me flip to the answers again. Looks like it comes out to be choice B, 19,500. Any questions there on 93? All right. Let's move all the way back towards the beginning to number 4. All right, number 4, we want to find out where the x coordinate of the point on the curve y equals x squared minus 2x plus 3. We want to find out when that is, the tangent of that is perpendicular. So we have the tangent line perpendicular to the line x plus 3y equals 3. So first off, we need to find the slope of this line. So that should be y equals negative x plus 3 over 3, the slope of negative 1/3. The perpendicular slope then should be 3, which means our tangent line has to have a slope of 3, which means that y prime, which is 2x minus 2, needs to equal 3, which means that x needs to be 5x. Any questions there on number 4? All right. The next one is 7. We do 7 already? No, we didn't do 7 already. Okay, 7. We're looking at the integral from 0 to 6 of the absolute value of x minus 4 dx. Well, we don't really have a formula to integrate absolute value. So the easiest thing to do is just, well, we know what the graph looks like, so we just need to find the area under the curve. X minus 4 absolute value is just absolute value shifted over 4 units. So this is at 4. And we'll just do each piece of this separately. We'll do this piece, and then the piece from 4 to 6, which, since these are just absolute values, this is 4. That's 4 to 6. That's 2 units, which makes this 2 units. And our area should just be 1/2 of 4 times 4 plus 1/2 of 2 times 2. And what does that give us? That gives us 8 plus 2 gives us 10. Any questions there on number 7? All right, next one we are looking at is number 9. We're looking for the maximum value of the function f of x equals x to the 4th minus 4x cubed plus 6 on the interval from 1 to 4. So in order to figure out the maximum value of this, we need to take the derivative of it. F prime should be 4x cubed minus 12x squared. First, we'll set this equal to 0, and we would see when it's undefined, but it's never undefined. So it's equal to 0, 4x squared times x minus 3. So that'd be x equals 0 or x equals 3. We can immediately ignore x equals 0 because it's not on our interval. And since we're looking for the absolute max, we also need to look at the endpoints. Now we can do a sine chart to start with. So if we have 1, 3, and 4, if we plug in something between 1 and 3, that's something like 2. And if we plug that in, this is a positive times a. Oh, somebody's saying something. Let's see here. Oh, that's just another question. Okay. If we plug in between 1 and 3, we get 2. Right. That's 2 times this is positive and that's negative. So we're negative, so we're decreasing. And from 3 to 4, like 3.5, we're going to get a positive and a positive, so we're increasing. And so it's asking for the maximum value, which means that since this is a closed interval, we have to check the endpoints. Clearly, the absolute max is not at 3. It's either at 1 or at 4. So we have to evaluate f of 1 and f of 4. F of 1 is 1 minus 4 plus 6, and f of 4 is 4 to the 4th minus 4 times 4 cubed plus 6. That's negative 3 plus 6, which is 3. And this is 4 to the 4th minus 4 to the 4th, which is 0, plus 6, which is 6. So our absolute maximum value ought to be 6. And it's quite possible that you might have got that one wrong because you didn't check for your sine chart and you just said, oh, it's at 3. You plugged in 3 and found your value. And I'm sure that was an answer choice. So. Any questions there on number 9? That makes sense to everybody? All right. Next one is number 12. So number 12, we got sine x equals natural log of y. So if sine of x equals natural log of y for x is less than pi greater than 0. Hold on one second. Okay, sorry about that. So talking about x between 0 and pi, and we're looking for dy dx. So in order to find dy dx, we can do one of two things. One, we could exponentiate both sides of this to just turn this into e to the sine x equals y, and then take the derivative of e to the sine x, which is e to the sine x times cosine x. Well, that will just be our answer, which looks like that's answer choice A. So that was one way we could do that. The other option is we could have started at just in a different color since I'm going to do it slightly differently. We could have said sine x equals ln y, and we could have just took the derivative with respect to x on both sides. So 1 over y dx, which would then give us dy dx equals y cosine x. And then you'd have to go in and replace the y with e to the sine x. The implicit way, or solve for y initially and then get the same value. Everybody good there with 12? Any questions on 12? All right. Next one will be 14. We are looking for the equation of the tangent line to e to the x ln x at x equals 1. So equation of the tangent, so we need to find a point. So y of 1 ought to be e to the 1 times ln 1. Well, ln 1 is 0, so that's the point 1, 0. And then we need a slope. y prime ought to be the derivative of this, which is e to the x times the derivative of ln x, plus the derivative of e to the x, which is e to the x, times ln x. And we'll evaluate that at x equals 1. So that's e to the first, or e over 1, plus e to the first times 0. So just e. So y prime is e. Got to be y minus 0 equals e times x minus 1. And they distributed that out to get e x minus e, I think. No, they didn't. Never mind. All of them were distributed except for the correct answer choice. Choice C. Any questions there on 14? All right. Making our way through here. 17. Did we do 17 already? I don't remember now. I remember doing this one earlier today, but I don't remember if I did it in this class. No. Okay. So 17, we're looking at f of x is x squared. If x is less than or equal to 2, f of x is 4x minus x squared. If x is greater than 2, we want to integrate f of x from -1 to 4. Since there's a break in the function at 2, we just separate it at 2, -1 to 2 of x squared dx, and then 2 to 4 of 4x minus x squared dx. And from there, you just integrate x cubed over 3 from -1 to 2, 2x squared minus x cubed over 3 from 2 to 4. And you evaluate 8/3 minus -1/3, and then plus, I'll just write it down here. Let's see, what does that become? Plus 32 minus 64/3 minus 8 minus 8/3. And then you simplify. What is that? 9/3 is 3. 35 minus 8 is 27. Minus 64/3 plus 8/3, so minus 56/3. That's 81 minus 56, which is 25/3. Good or no? Any questions there on 17? All right. Next one. If my pen will work. There we go. All right, next one is 19. So for 19, we got a rectangle, has a side on an x-axis, and it's inscribed into a triangle. It's formed by y equals x and y equals 0, so the y-axis, and 2x plus y equals 12, which is y equals -2x plus 12. Just write it that way for now. So we're looking at a rectangle that has been inscribed inside of that triangle. And we need to find the, what do we need to find? The maximum area? Yeah, the area of the largest such rectangle. So we're looking for the maximum of that rectangle. So we need to find the area of that rectangle. So first off, the coordinates here and here are a little more difficult to find. Let's just call them x1 and x2. But our height here is just going to be y. So our area ought to be x2 minus x1 times y. So we're going to want to do this all in terms of y, because I can rewrite x2 and x1 just as, they're just x values. So I can rewrite them in terms of the y function that we get, like y equals x, y equals 0, that's y equals x, and y equals -2x plus 12. So for this one, this is x1, right? So x1 is just equal to y, and x2, well, x2 ought to be 12 minus y over 2. So we end up with our area formula is 12 minus y over 2 minus y times y. And we can simplify that down. That's 6 minus a half y. If I multiply the 6 by the y, that's 6y. The minus a half y and the minus y is minus 3 halves y, and then minus 3 halves y squared. And we just want to know, when is this at a maximum? So we'll take a derivative. A prime is 6 minus 3y. Set that equal to 0. Should be at a max when y is equal to 2. And we'll just check and make sure the lowest y value that we're talking about here is 0. The highest is this intersection point, which would be when x1 is equal to x2. So that'd be when y is equal to 12 minus y over 2. Solve that, that's 2y, 3y equals 12, or y equals 4. So you can check and make sure this is a max by using a sine chart if you want here. Plug in 1 to this, you get a positive, so we're increasing. Plug in 3 to this, you get a negative, so we're decreasing, and we see that it's a max when y is 2. Alternatively, you could have found the second derivative. That's -3, which is less than 0, which tells you it's a max. So it occurs when y is 2. When y is 2, our area ought to be 12 minus 2 over 2 minus 2 times 2. And 12 minus 2 is 10. 10 over 2 is 5. 5 minus 2 is 3 times 2. Gives you a max area of 6. Choice A. That was a fun one. Any questions on 19? All right. Let's do number 20. You guys always have more questions than second period does. I don't know if that's good or bad. We're looking for the value of the first quadrant point on x squared minus y squared equals 1 that is closest to the point 3, 0. So the distance between a point, we'll just call it a point xy, and a point 3, 0 ought to be the square root of x minus 3 squared plus y minus 0 squared. That should be the distance between them. We want to minimize this distance. And if we think back to a long time ago when we did optimization, I made this point a couple of different times, that if you're looking for the minimum of a function that is all inside of a square root, you can also minimize just the square of it, and they will both occur at the same x value. So let's turn y squared into terms of x. Y squared is equal to x squared minus 1. And so this is our square of our distance, and we will minimize that. 2 times x minus 3 plus 2x, or 4x minus 6. And it occurs when x is 3 halves. And we can take a second derivative to see if that's a max or a min, since that's probably easier. The second derivative of 4x minus 6 is 4, which is greater than 0, which tells us it's a minimum at x equals 3 halves. Any questions there on number 20? All right, let's see, 22. No, we did 22. There's an overlap. Exciting. All right, next one is 31. So 31 says we got the curve 2x squared y plus y squared equals 2x plus 13. Tells us this goes through the point 3, 1. And we want to use the tangent line at 3, 1 to approximate the value at x equals 2.8. So first off, we need to write the equation of the tangent line, which means we need to find the slope of this at 3, 1, which means we need to take the derivative of this. Clearly, we need to do that implicitly. So this is two functions being multiplied together, so product rule. 2x squared dy dx plus 4x times just y, then plus 2y dy dx equals 2. Anybody, any issues with the implicit differentiation there? Everybody good with that? All right. We'll subtract the 4xy over. When we do that, everything that's left on the left-hand side has a dy dx in it, so we'll factor out the dy dx and then just divide by the 2x squared plus 2y. So there's our derivative. If we want to, we can divide it all by 2 just to make arithmetic easier, but you don't have to. Evaluated at 3, 1, we end up with 1 minus 6 over 10. So that's negative 1/2. So our equation of our line ought to be y minus 1 equals negative 1/2 times x minus 3. And we're asked to approximate the value of 2.8. So that should be y minus 1 equals negative 1/2 times 2.8 minus 3. 2.8 minus 3 is negative 0.2. The negative 0.2 and the negative will cancel, so it's just 1/2 of 0.2, which tells us y minus 1 equals, what did I just say, 0.1? And so y equals 1.1, which is choice D. Any questions there on 31? All right, I think that's probably a good place to stop. So I've taken a picture of what's left in there. We'll get around to those at some point. We got a few more to do. Some of them are overlaps, I know, but we'll take care of those at some point. That is where we will end today since we're already over time.